Hello, everyone, and welcome to day 30 of Jamb Physics in 40 Days series. And just like that, the series is almost coming to an end. Thanks to everyone that has been part of the series from day one up until this very moment. After today, we have just 10 more days and the series will be over. So, thank you so much for the love and support, for always making it a date to check out the videos for each of the days, and also ensuring that you are subscribed to the channel, ensuring that you share and like the videos we are making. Thank you so very much. To those of you who are seeing this video for the first time, this is Jamb Physics in 40 Days, a series that is brought to you by Oyalen, where we believe that when you dedicate within 30 to 45 minutes of your time daily going through our video, you should be able to get all the necessary tools that you would need to help you ace Jamb Physics. So peradventure, you are a candidate preparing for the Jamb exams, and one of the subjects you are to write in the Jamb exams is physics. Then this video is specifically made for you. So trust me, you want to check out all the videos in the series from day one to the end, because in each of those videos, what we have done is that we look at the individual topics in the Jamb Physics curriculum, then we give you a crash course to it, telling you what is expected of you by Jamb, and then we solve past questions while giving you tips that will help you solve questions like that with high accuracy each time. So when you are able to look at all the videos in the series, we guarantee that you should be able to score 90 plus in your Jamb Physics exam. It just takes dedication, ensuring that you are going through the videos one after the other and learning. And please, if you come across any challenging topic or you see a question that you don't quite understand very well, you need more clarity, please always drop it in the comment section. We are totally here for you. So we'll attend to all of your questions. Just keep them coming and you will get answers to everything that bothers you on what we are doing so far. And please, if you are not subscribed to the channel, ensure you click the subscription button. Just click it. It's just going to take a second of your time. That will be your way of helping us to continue to make more videos like this. And you can also hit the notification bell icon so that you get alerted every time we put out a new content. And also, to improve your practice time, you can use the Exam Phone app by clicking the link in the description box of this video that will help you download the Exam Fun app that is created with you in mind to infuse a bit of fun into your study time and also make your studies a rewarding one. So you learn and you also earn when you use the Exam Fun app. So please download the app today. And please don't forget to share our content with your contact list. We want to ensure that we reach a wide range of audience that are in need of videos like this. So please keep on sharing and encourage them to be subscribed to the channel as well. Thank you so very much for being part of this series. To the business of day 30, what we're going to be looking at in this video is capacitors. And what is expected by Jamb of all candidates is that you should be able to understand the concepts in the following topics. They expect that you should be able to mention the types of capacitors and functions of capacitors. Now, when we talk about types of capacitors, some of the types include ceramic capacitors, electrolytic capacitors, non-electrolytic capacitors, film capacitors, tantalum capacitors, and so on, right? And what capacitors do, the number one function that we usually mention is that they are used to store electric charges. But capacitors perform functions beyond just storing electric charges. They could also be used to smoothing voltages. They can also be used to block DC, that is direct current, thereby allowing only AC. And then they are also used to filter signals, like in your amplifiers, they use capacitors to filter signals there. So they expect you to be able to state those things. And then secondly, they expect that you should be able to explain the concept of parallel plates capacitors, do some workings around that as well, and also be able to calculate the capacitance of a capacitor. Now, that is given as C equals Q over V, where C is the capacitance, Q is the quantity of charge, and V is the potential difference or voltage applied. So this is the equation that works for capacitance of a capacitor. Now, they also expect that you should be able to show the relationship between the capacitance of a capacitor with the area of the plates, the separation of the plates, and the medium of the plates, that is the dielectric that is separating the plates. So you should be able to state the relationship there, and that is given as C equals permittivity multiplied by area multiplied by the distance separating the plates. Now, if it is free space, that is, it is a vacuum that separates the plates, this permittivity then becomes what is known as permittivity of free space, E naught. Otherwise, it will be stated what type of permittivity of the dielectric that is being used. And each of them have their separate values. So please always look out for it. It's not always a particular value. It depends on the nature of the dielectric that separates the plates, right? So, but this equation works each time you are to find the capacitance of a capacitor when you are given the distance separating the plates of the capacitor, the area of the plates, and then the permittivity of the material of the medium separating the plates. And then they also expect that you should be able to calculate the capacitance of capacitors in series and in parallel. Now, take note, when capacitors are in parallel, right, the equivalent capacitance or total capacitance is given as C1 plus C2 plus Cn. That is, if there are 3, 4, 5, 6 capacitors connected in parallel, this is how we find the equivalent capacitance or total capacitance. Now, how would you know if they are in parallel? This is when a capacitor has two leads, right? This is the symbol for a capacitor. It has two leads. So let's call this C1, for example. If you are connecting it in parallel with another capacitor, the two leads are going to be connected to the two leads of the next capacitor. That is like this to another capacitor, C2. This is parallel connection. So the equivalent capacitance or total capacitance will then be C1 plus C2. That is for parallel connection. Now, when they are in series, it means it's only one lead that is connected to the next lead of the next capacitor. That is, when you have a capacitor like this, C1, connected to another capacitor like this, C2, and so on like that to C3. This is called series connection. And the total capacitance, 1 over Ct, is given as 1 over C1 plus 1 over C2 plus 1 over C3. Now, if there are more than 3 capacitors, of course, we continue like that, plus 1 over C4 plus 1 over C5 until you have captured all the capacitors. Now, the trick with working questions like this is that sometimes the connection you are going to be given is going to combine series and parallel. It is important that you are able to identify which of the connection is the most visible one there. Because in the end, it could just be series that you are looking at in the end. So every other one that is in parallel, you have to collapse them to bring them into one capacitance that you now connect in series with the others, and then find the total capacitance using the series connection. And then there are times that you are going to see some in series, but the overall connection is in parallel. So those in series, you have to find their equivalent capacitance and then put them in parallel with the rest so that you can then use the parallel connection to get the total capacitance. So it all lies in knowing what is the overall connection in a circuit that you see, okay? And that will be how you can solve for capacitance of capacitors in series and in parallel. Now, finally, Jamb expects every candidate to be able to calculate the energy stored in a capacitor. Now, the general equation for this is given as the energy equals half CV squared. Now, we already established that C equals QV, right? That means this equation can change. If I substitute C now with Q over V, you now see that E therefore becomes 1 over 2. Instead of C, you have Q over V multiplied by V squared. So this takes out this. So what we have is half QV. Okay? This same thing now can still be substituted such that I will write it in terms of V. You know, V will then be Q over C, right? I can now say 1 over 2q multiplied by, instead of v now, I'll say q over c, right? So this becomes 1 over 2 q squared over c. So these three equations, that is this, and this, all work for the energy stored in a capacitor. So it's up to you to look at what information you are given in the question to determine which of these three equations you will use to find the energy stored in a capacitor. Now, this is not with all the details. Of course, there are some things I would have skipped while talking. So please check out our video where we talk about capacitors and capacitance in greater detail. Now, in that video, we break it down such that every detail is explained, and we give multiple examples that help you solve different type of questions that you can find on this topic. However, for the purpose of prepping you for Jamb, we're going to be looking at some past questions on capacitors and capacitance now. And while we are solving, I'll be giving some tips that will help you solve those kind of questions with greater accuracy every time you find them. So if you're ready, get your materials and then let's solve some questions on capacitors and capacitance. The resultant capacitance in the figure above is, now I did mention at the beginning of the video that when you're asked to find the total capacitance or equivalent capacitance, or in this case resultant capacitance of a set of capacitors connected in series or in parallel, that you have to look out for the overall connection here. So what we see here is a series connection, but there's a bit of parallel connection in between it. So the total capacitance will be done using the series capacitors connection. But first, we have to break down this parallel connection to get a single capacitor that will give us the equivalent of these two. So if this is C1, C2, now C3, we have C3A, C3B, right? And then C4. Now these are in parallel, so let's find the parallel connection first. So capacitance in parallel would then be the sum of the capacitors. So we have 2 microfarad plus 4 microfarad, which will give us 6 microfarad. Now what we have is 2 microfarad, 3 microfarad. Now this has become 1, which is 6 microfarad, and then the final one, which is under 4 microfarad. Now the equivalent capacitance or total or resultant capacitance 1 over C would then be 1 over 2 UF plus 1 over 3 UF plus 1 over 6 UF plus 1 over 4 UF. Now what does this mean? It means 1 over C equals, if you take LCM here, that is 12 UF, and then this will go here, so we have 6, just 6, then plus this will go here 4 times, so plus 4, plus this will go here giving us 2, plus this will go here giving us 3. So what we have now is 6 plus 4, which is 10. 6 plus 4 is 10. 10 plus this is 5, so that's 15 over 12 UF. Now let's come here. So we see that 1 over C equals 15 over 12 microfarad. Now when you flip this, you can also flip this side such that we now have C over 1, which is C, equals 12 microfarads divided by 15. Now what is 12 divided by 15? That is 0.8. So we have 0.8 microfarads, and that is option B. A supply of 400 volts is connected across capacitors of 3 microfarad and 6 microfarad in series. Calculate the charge. So let's solve this, but to solve, let's visualize. I'll first create a circuit for this. So we have 2 capacitors in series connected to a voltage source, 400 volts. This is 3 UF, this is 6 UF. Okay, so you see that the current from the voltage source is going to pass through both of them, so they're going to have the same current. And since Q equals IT, it means that they're also going to have the same quantity of charge. Now I'm showing you this so that you understand that when you are solving for capacitors that are in parallel, the current is going to branch, so meaning that each of the capacitors are going to have different quantity of charge on them. So in that case, you will know how to solve for the charge, individual charge, the total charge, and then use that to get your, in this case, the charge in the circuit. Okay, so but since this is in series, they have the same charge, so I can just go straight to find the charge by finding the total capacitance here. Now the relationship is that Q equals CV, but I need C because this C is the total capacitance. If this were in parallel, they would have the same voltage, but here they have different voltage, right? So but to be able to solve the total charge here, Q, I have to apply this voltage of 400 volts and then the total capacitor, so I have to bring these two capacitors and make them one. So what do we do here? First find the total capacitance. So 1 over C equals 1 over C1 plus 1 over C2. Now this same thing can be written as C total equals C1 times C2 over C1 plus C2, which would give us 3UF times 6UF over 3UF plus 6UF. Now this would give us 18 over 9, everything in UF, which is 2UF. Remember that this U here is micro, which is times 10 raised to the power minus 6. So when we find the quantity of charge Q, we'll then apply that as 2 times 10 raised to the power minus 6 multiplied by the voltage source, which is 400. Now this would give us 800 times 10 raised to the power minus 6, which when you bring to standard form will be 8 times 10 raised to the power. So this is 1, 2. So add 2 rather to minus 6 and then it becomes minus 4. And this is measured in coulombs. So 8 times 10 raised to the power minus 4 coulombs, and that is in option A. This question says we should calculate the effective capacitance of the circuit in the diagram given. And when you look at the diagram given here, remember that to catch the kind of connection, you have to look at how the leads are connected. Now, these 2 microfarad, these 2 microfarad capacitors, you see that all their leads are connected. That tells you that these 3 like this are in parallel. Okay, but this one, only one lead is connected, only one lead of this is also connected, so that is series. Now to see the overall connection, we have to see the beginning and the end of the circuit. The circuit starts at either here or here, which is then connected in series to these 3 that are in parallel, which is then connected in series with this other one here. So we see that the overall connection here is series connection. So basically what we are having is 2UF connected to these ones that are in parallel and then in series to the third one like this. So remember, this is also 2UF, this is another 2UF, this is another 2UF, then this one is 3UF. That is what this connection is, exactly like that. So 3 connected in parallel and these ones in series with it. So all we have to do to find the effective capacitance is to first break down the one in parallel such that we'll have it in series. So when we break that down, the capacitors in parallel will then be 2UF plus 2UF plus 2UF, which would give us 6UF. Now that brings this diagram down to now be like this, where we have 2 microfarad here, 6 microfarad here, and then 3 microfarad here connected in parallel. So 1 over total capacitance is then 1 over 2 plus 1 over 6 plus 1 over 3. So 1 over C total is then LCM is 12. This would go 4. No, this is 6 rather. This would go twice. And then this would go 4 times. So what we have here is 12 over 12. So the total capacitance is then 1 microfarad. And the correct option to go for is D. Capacitors are used in the induction coil too. Now, let's consider the options and then pick out the one that is correct. However, I'll also talk about the other options and why they are not correct so that you don't make any mistakes when you are picking your answers. Now, the first option says to control circuit. Control circuit is more like switching a circuit, which is more of the function of a transistor and not a capacitor. So this is for transistor. Now, to prevent the distortion of electric field, now this does not even have anything to do with capacitors or induction coil whatsoever. So it's out of context entirely. So it does not work with the kind of question line that we have. So it's out of it. And then, yes, option C says to prevent electric spark. Now, this is one of the reasons why capacitors is used in induction coil, which is to actually prevent electric spark. Another reason would be that it is used also to absorb or to take in a sudden voltage spike. Whenever the voltage spikes up, the capacitor is going to accept that voltage and take it in. So this is the correct answer here. And then this says to dissipate energy. Capacitor is used to temporarily store energy. To dissipate energy, you will be needing a resistor for that. So it's resistors that dissipate energy. Capacitors store energy. So the answer here remains option C. When a piece of rectangular glass block is inserted between two parallel capacitors at constant plate area and distance of separation, the capacitance of the capacitor will. Now, consider this. When the glass block is not inserted yet, the relationship between the capacitance of the capacitor, the area, and the separation of the plates is given as this, where we have capacitance equals, now because there's nothing there to be permittivity of free space multiplied by area all over distance. Now, by the time you put the glass block, something is going to change. Remember, the area remains the same, it's constant, the distance is the same, but this now becomes here, where we have to factor in the permittivity of the dielectric, which is the glass. And the permittivity of glass is greater than 1. So as a result, it's going to increase what we know as the capacitance of the capacitor. So therefore, the correct answer to pick here is option A, which says it will increase the capacitance. If you're yet to be subscribed to the channel, kindly take a second of your time to click the subscribe button so that you can help us to continue to make more helpful content like this. And don't forget to also hit the notification bell icon so that you always get alerted every time we put out a new content. And also ensure that you like and share the videos so that we can reach even more audience that are in need of content like this. And if you have any question at all that you'd like to ask us, please put it in the comment section and we promise to attend to every one of your comments. Now, this question says, the capacitance of a parallel plate capacitor is 20 microfarad in air and 60 microfarad in the presence of a dielectric. Now, what is the dielectric constant? Now, there are ways we can derive the solution to this, but they ultimately lead to the fact that the dielectric constant is a ratio of the capacitance in dielectric over the capacitance in air. That is, when there's the dielectric, we have 60 microfarad, and then we're going to divide that by the capacitance of the parallel plate capacitor in air, which is 20 microfarad. Now, when we divide this, this is going to give us 3.0. So the correct option here is C. 3 capacitors of capacitance 2 microfarad 4 microfarad and 8 microfarad are connected in parallel, and a potential difference of 6 volts is maintained across each capacitor. The total energy is, now before I solve this, let's look at a diagram for this so that it can help you understand the concept behind it. So we have 3 capacitors in parallel connected to a voltage source of 6 volts. Now where this is 2 microfarad, 4 microfarad and 8 microfarad. Now when you consider this, you see that the voltage applied across is the same for each of them, that they all maintain the same V, the same V, the same V. Okay, and for us to be able to calculate the energy stored, we have to find the total capacitance. So this is what we do. The solution is going to be the energy equals half CV squared. So this C being the total capacitance. So let's start with that. The total capacitance, because it's in parallel, will be the sum of the individual capacitance, which is 2 microfarad plus 4 microfarad plus 8 microfarads. And this is going to give us 14 microfarads. Now let's solve for the energy. The energy stored is then 1 over 2 multiplied by 14 times 10 raised to the power minus 6 farads. And then we multiply this by V squared, that is 6 squared. Now this gives us 1 over 2 times 14 times 10 raised to the power minus 6 times 36. Now when we break it down, 2 here 1, 2 here 7. 7 times 36 is going to give us 252. Then times 10 raised to the power minus 6. Now let's bring it to standard form. To bring it to standard form, this will move 1, 2. So we'll have 2.52 times 10. Now this is minus 6. So plus 2, it becomes minus 4. And energy is measured in joules. So 2.52 times 10 raised to the power minus 4 joules. And that is option C. The figure above shows 3 capacitors, 2 microfarad, 3 microfarad and 6 microfarad connected in series. If the potential difference across the system is 12 volts, the potential difference across the 6 microfarad capacitor is. Now, looking at this diagram, the current from the cell is going to move through all the capacitors, where this is capacitor C1, C2, C3. C1 is 2 microfarad, C2 is 3 microfarad, and C3 is 6 microfarad. Now, one thing is certain, this voltage is going to share itself across each of these, such that we have V1 here, V2 here, V3 here. So basically what we are looking for is V3. Now, in order to get that, we must first find the quantity of charge that goes across, that they store, that all the 3 capacitors are going to store. And they're going to store the same charge, so therefore we can solve for Q straight using Q equals CV. But for that, we have to find the total capacitance first. So because total charge should equal total capacitance multiplied by total voltage, which is potential difference, which is 12 volts. So let's start by getting the total capacitance. The total capacitance, 1 over C, because it's in parallel, is in series rather, is then 1 over C1, which is 2UF plus 1 over 3UF plus 1 over 6UF. Now, when you take LCM here, the LCM is 12. And then this here, that will give us 6 plus 4 plus 2. So 1 over C equals, when we add this up, we have 12 over 12 UF. Remember, this is in UF. So by the time you invert this implies that C equals 1 UF. That's the total capacitance here. Now we can then find the total charge Q. Q equals CV. Therefore, that will be 1 UF multiplied by the total potential difference, which is 12 volts. And when we do this, we're going to get 12 times 10 raised to power minus 6 because of the micro symbol here. And of course, this is measured in coulombs. Now we have the charge. We can now begin to solve for the individual voltage across each of the capacitors. Now, since this is for C3, I'm going to work with C3. So that means that the V3 is going to be Q over C3. The same thing applies to C2. If you are working for C2, V2 is going to be Q divided by C2. And the same thing applies to V1 because V1 will be Q divided by C1. So let's work with this. Q is already given as 12 times 10 raised to the power minus 6 from what we calculated. This is in coulombs. Divided by the capacitance of capacitor 3. That is 6 times 10 raised to the power minus 6 farad. So this cancels out. Then V3 is therefore 12 divided by 6, which will give you 2, and is measured in volts. So the correct option here is option C. This question is similar to what we just solved, except that this time we are now asked to find the potential difference across each of the capacitor, that is C1, C2, and C3. That is the potential difference V1, potential difference V2, and potential difference V3 across the individual capacitors. So just like we did, we're going to start by getting the total charge. The total charge Q is total capacitance times total voltage. And the total capacitance, C total. To get this, we have to apply that. Let me wipe this quickly. So 1 over C equals 1 over 2 plus 1 over 6 plus 1 over 3. Now LCM is 12. This would give us 6 plus 2 plus 4. So what we have here is 12 over 12. So C total is therefore 1 microfarad, which implies that Q equals 1 times 10 raised to the power minus 6 multiplied by 12 volts. And when we do this, we get 12 times 10 raised to the power minus 6 coulombs. So now that we have this, let's begin to find their individual voltages. So V1 is going to be, still from this formula, so Q now, because they have the same quantity of charge, over C1. So let's work with this. Q is 12 times 10 raised to the power minus 6. Now we're going to divide that by C1, which is 2 times 10 raised to the power minus 6. And this would give us 6 volts. Now V2, Q over C2, that is 12 times 10 raised to the power minus 6 divided by C2, which is 6 times 10 raised to the power minus 6. And this would give us 2 volts. And then finally V3, which is Q divided by C3, is going to be 12 times 10 raised to the power minus 6 divided by C3, which is 3 times 10 raised to the power minus 6. And this is going to give us 4 volts. So what we have is 6 volts, 2 volts, and 4 volts respectively. So the correct answer is option D, which is similar to this. So we go with D. This question says, the diagram above shows two capacitors P and Q of capacitance 2 microfarads and 4 microfarad respectively, connected to a DC source. Now, the ratio of the energy stored in P and Q is, so we have to find the ratio of the energy stored in each of the capacitors. Now, what we need to observe here is this. Now, you see that these two capacitors are connected in parallel. Now, what this implies is that V equals V1 equals V2, the same potential difference is going to be across each of the capacitors, and it is similar to the potential difference connected in the entire circuit as it is. And the energy stored, E, equals half CV squared. Now, do not forget that in this case here, you have to look at their individual capacitors. the capacitance of each of the capacitors when you are calculating this. So let's put that into calculation and see what we're going to get, especially with the ratio of the energy stored in P to Q. So let's start by the energy stored in P. So energy in P is going to be 1/2. Now, this will be capacitor 1, but since it's called P, so it will be Cp multiplied by V squared. The same voltage goes across, so we just call it V. Now, when you put this, we can call this equation 1. Now, moving to EQ. EQ is 1/2, and then we have CQ V squared, equation 2. Now let's solve each of them and see what we get. So with this one, we're going to be having 1/2 times Cp is what? 2 times 10 raised to the power minus 6, then V squared. Now from here, 2 here, we have 1. So what we have is 1 times 10 raised to the power minus 6 V squared. Now for this other one, we're going to be having 1/2 times Cq is 4 microfarad, so times 10 raised to the power minus 6, and then V squared. 2 here 1, 2 here 2. 2 times 1 will give you 2, so 2 times 10 raised to the power minus 6 V squared. Now, the ratio of the energy stored in P to Q, that is E of P over E of Q. That's going to give us, so E of P, 1 times 10 raised to the power minus 6 V squared, all over E of Q, 2 times 10 raised to the power minus 6 V squared. So, see, V squared cancel V squares. 10 raised to the power minus 6, 10 raised to the power minus 6. So what we have is 1/2, which means the ratio is 1 to 2. So the correct option here is D. If you're yet to be subscribed to the channel, please kindly take a second of your time to help us click the subscribe button. It is important to us that you are subscribed to the channel, because that is how you help us to continually make more helpful content like this. So please click the subscribe button, and you can also hit the notification bell icon so that you get alerted every time we put out a new content. And don't forget that if you have any question at all you'd like to ask us, we are waiting on your question. Please put them in the comment section. We will definitely attend to all of your comments. And please keep liking the videos, and don't forget to share them with your contact list so that we can reach a wide range of audience that need content like this to be able to ace their Jamb physics. So please keep sharing, like the videos, and if you are not subscribed, kindly click the subscribe button. Thank you so very much. Now let's consider this question on the board. It says a parallel plate capacitor has a common plate area of 5 times 10 raised to the power minus 8 meters squared, and a plate separation of 2 times 10 raised to the power minus 3 meters, and assuming free space. So what is the capacitance given that permittivity of free space is 9.0 times 10 raised to the power minus 12 coulomb square per Newton per meter square? Let's start off by writing out the facts from this question. So what we are looking for is the capacitance is unknown, but we are told that the plate area is 5 times 10 raised to the power minus 8 meters squared. The plate separation D is 2 times 10 raised to the power minus 3 meters, while the permittivity of free space is 9.0 times 10 raised to the power minus 12 coulomb square per Newton per meter squared. Now, all we have to do is find the capacitance by using the relationship between all these 4 parameters. And C is supposed to be E naught A over D. Now, when we put in the values of each of these parameters, we're going to be having 9 times 10 raised to the power minus 12. Multiply that by the area, which is 5 times 10 raised to the power minus 8, all divided by the separation, 2 times 10 raised to the power minus 3. That means the capacitance C equals 9 times 5, that's 45, divided by 2, all times 10. Applying the law of indices now, this will be minus 12 minus 8. Now this is minus 3. When it goes up, it becomes plus 3. So what does this give us? So C equals 45 divided by 2, that is 22.5. So multiplied by 10 to the power of minus 12 minus 8 is minus 20. Minus 20 plus 3 is minus 17. Now we can move this decimal place forward by one step, which means we'll add 1 to this. It then becomes 2.25 times 10 to the power of minus 16. And capacitance is measured in farads. So the correct option here is option C. The purpose of a dielectric material in a parallel capacitor is to, now when we talk about the dielectric material, there are two functions that are very prominent of what it does. Now the first thing that we put into consideration is that it insulates the plates from each other, and then secondly, due to the relative permittivity of the dielectric material, it will also increase the capacitance. Now, of these two things that I've mentioned, you can see them in option A and option C, right? Of these two, the main purpose for choosing the dielectric material is to determine to what ratio you want to increase the capacitance. Because they are from 1 and above. So if you use that has a relative permittivity of 1, it will be the same. If you use one of 1.5, it will multiply the original capacitance by 1.5 and so on. If you use times 2, it will increase it by a fold of 2. So that becomes the main purpose why you choose the dielectric material for your parallel plate capacitor. So that means, despite the fact that these two are true, the one they are going to pick in this question is option A because it serves as the main purpose. A parallel plate capacitor of area 10 cm square in a vacuum has a capacitance of 10 to the power of negative 2 microfarad. What is the distance between the plates given that permittivity of free space is 9 times 10 to the power minus 12 farad meter? Now, first thing we want to do here is to ensure everything is in the correct SI unit. Then we'll plug that into the equation and then we can solve the distance. So let's start. First, we have the area, which is 10 centimeters squared. It's basically the same as saying 10 multiplied by 1 centimeter squared. And bringing this into meter squared will mean we have 10 times 1 centimeter squared is 1 times 10 raised to the power minus 4. Then this brings it to meter squared. Now when you multiply this, you get 10 times 10 raised to the power minus 4 meter squared, or basically 1 times 10 raised to the power minus 3 meter squared. That is for the area. Now every other thing seems to be in the SI unit, except that we have to express this as a multiplier rather than just writing it as a symbol. And that is the capacitance. So capacitance, which is 10 raised to the power minus 2 microfarad, will then become 10 raised to the power minus 2 times 10 raised to the power minus 6. Then this is in farad. Applying law of indices, this becomes 10 raised to the power minus 8 farads. And permittivity of free space remains what it is, which is 9 times 10 raised to the power minus 12 farad meter. So all we have to do now is just put all of this into the equation. So since capacitance is E naught A over D, this implies that D becomes E naught A over C. So the distance is therefore, now E naught, that's 9 times 10 raised to the power minus 12. Multiply that by the area, which is 1 times 10 raised to the power minus 3, all divided now by the capacitance. And capacitance is 10 raised to the power minus 8. So let's see what this gives us. 9 times 1 is 9, divided by 1 is still 9, times 10. Now apply the laws of indices. This is minus 12 minus 3. Then this becomes plus 8. So D becomes 9 times 10. Now minus 12 minus 3, that gives us minus 15. And minus 15 plus 8 will give us minus 7. And this is measured in meters. So our answer is 9 times 10 raised to the power minus 7 meters. And that is option B. Two capacitors of 6 microfarad and 8 microfarad are connected in series. What additional capacitance must be connected in series with this combination to give total of 3 microfarad? So basically now we are having the first one as 6 microfarad. The next one that follow is 8 microfarad. Now we want to connect a third one, so let's say that's C, such that the total C is going to be 3 microfarad. So let's solve this. Remember, this is in series, so the total capacitance is 1 over C. So that will be 1 over C equals 1 over C1 plus 1 over C2 plus 1 over C3. So let's apply that. 1 over total capacitance is 3 equals 1 over 6 plus 1 over 8 plus 1 over C. So that's C3. Okay, so let's work with that. Now what we have here is 1 over 3 equals, the LCM here is 24C3. So this here will go 4 times 1, so 4 plus, remember there's C3, 4C3. Now this will go 3 times 3C3, so that will be 3C3 plus C3 here, that will give you 24. Now when we work with this, we have 1 over 3 equals 7 C3s plus 24 all over 24 C3. Now you can cross multiply. So we have 24 C3, because multiplied by 1 remains the same, equals 3 into 7 C3s plus 24. Now this will give us 24 C3 equals 21 C3 plus, this times this, that's 72. Okay, so collecting like terms, 24 C3 minus 21 C3 equals 72, which means 3 C3 equals 72. So C3 becomes 72 divided by 3, and that will be 2, then 4. So 24 microfarad. So the correct option is C. A parallel plate capacitor separated by an air gap is made of 0.8 meter square thin plate and 20 millimeters apart. It is connected to 120 volt battery. What is the charge on the plate? Now to start with, the charge Q is given as CV. So we have to start with C so that we can then multiply that by the volt, which is 120. Okay, so to get the C, we're going to apply E naught A over D. Now this means we're going to be having 8.85 times 10 raised to the power minus 12, and then we multiply that by the area, which is 0.8, all divided by the distance separating them, that's 20 times 10 raised to the power minus 3. Now when you compute that, this would give you 3.54 times 10 raised to the power minus 10, and this is in coulombs. So now to find Q will then be this, which is 3.54 times 10 raised to the power minus 10. Then we multiply this by 120 volts. Now when you multiply this, it would give you 4.25 times 10 to the power of minus 8, and it is measured in coulombs. Now all the options there are in nano, so it means we have to bring this to times 10 to the power minus 9. So to do that, we have to move the decimal point forward by 1 step, thereby we subtract 1 from this. So we say Q equals 42.5 times 10 raised to the power minus 9 coulombs. Therefore Q is 42.5 nanocoulombs. So the correct option here is B. Now to put in more practice, I advise that you use the Exam Fund app, which is going to make your study time even more interesting, because it is created in such a way that it infuses fun into you solving different problems on different topics and from different subjects of your choice. And to add to this, you get rewarded by the number of questions you're able to solve correctly. So it makes it both fun and rewarding. So you do not want to miss this. So please click the link in the description box of this video to download the Exam Fund app today. And don't forget to always subscribe to the channel and also like our videos as well as share it amongst your contact list so that we can reach our goal of getting this helpful content to as many people who really need it. I want to say a big thank you to all of you for following the series so far. Don't forget that if you have any question at all, you can always put it in the comment section and we promise to attend to all of your comments as they come in. Thank you so much for following the series. I'll see you in the next one because it's not over yet. We keep going until we reach our goal. I'll see you in the next video.